Hello students, this is lecture 11 of MTH 201. In the last lecture we discussed chain rules, definition of a tangent vector to a curve on a surface, and we also discussed some differentiation rules. Today we are going to talk about two concepts primarily, gradient of a function and directional derivative of a function. So let us first define gradient of a function. So let f be a function of three variables and it takes real values, and suppose it's a differentiable. The gradient of f is a vector and it's denoted as del f or grad f, and it is defined as del f equal to fxi plus fyj plus fzk, which means that the ith component, the first component of this vector grad f is fx, which is the partial derivative of f with respect to x. The second component is fy, which is partial derivative of f with respect to y. And third component is fz, which is partial derivative of f with respect to z. So it's a vector, it gives you a vector. Similarly, if your function is a function of two variables, then you drop the third term. Okay? And this definition can be generalized to a function from Rn to R, where you get a vector which will have several components, and those components will be basically partial derivatives of the function with respect to all the variables. What is a vector field? A vector field in R3 is a function which goes from R3 to R3, which assigns a vector to each point in R3. Okay, we'll look at an example that it will be clear. But in R3, a vector field is a function from R3 to R3. Okay, so for every point you have a vector. So if you look at the gradient function, which is grad f takes a point in R3 to a vector, right, which is given by this vector. Therefore, it gives you a vector field. And this vector field is known as gradient field. Okay, and similarly on R2 you can define the same thing. It's important to note that grad f is same as the derivative matrix df, except that df is a row matrix and grad f is a vector. So remember, so recall that the derivative matrix df is what? It's a row vector. It has size 1 cross 3 and the entries are nothing but the partial derivatives fx, fy, fz. So when you write df, which is the derivative matrix, you write it as a matrix, whereas grad f is written as a vector. Okay, but the entries are the same. Okay. Let us look at this example where you are asked to sketch the gradient field of this function. So this function is from R2 to R. So what is gradient field? You compute the gradient of the function. But you need function to be differentiable. So this function is of course differentiable on R2 because if you compute the partial derivatives, they exist and they are both continuous on R2. Okay, so therefore the function is differentiable. It's a very nice function. What is gradient of f at the point x comma y? It's fxi plus fyj. What is fx? Fx is 2x and fy is minus 2y. So this is the gradient function. So to sketch the vector field at the point xy, so what did we say? What is a vector field? Vector field assigns to every point in R2 in this case a vector in R2, right? So how do you do that? So if you have to sketch the vector field, at each point x comma y in R2, you draw the vector gradient f with tail at x comma y. So you start at the point x comma y and you plot the vector which is the gradient vector. So this is an example. So let us look at a few examples. So if you take the point 1 comma 1, what is the gradient of f at 1 comma 1? It's 2 comma minus 2. So here 1 comma 1 point would be somewhere here. So at 1 comma 1 you plot the vector 2 comma minus 2. So 2 comma minus 2, where will it point? It will point in the positive, it will point towards which quadrant? It will point towards the fourth quadrant, right? Where x is positive and y is negative. Because x is positive 2, y is negative 2. So you place your cursor here or your pen here and plot a vector which is in this direction. Okay? So that's what we have done here. So if you look at any point which is in the first quadrant, then x and y are both positive. Therefore, the gradient will have the first component positive and the second component negative. Therefore, it will always point towards the fourth quadrant. And similarly, you can check for the others. So I would like you to spend a few minutes on this diagram. Take 2 points each in every quadrant and see what the vectors are and match it with the picture that is given to you. Okay. So if you have a point x comma y, where is x comma y? It's on the x-axis. What is the gradient of at the point x comma y? It's 2x comma y. So if you are in the positive x-axis, you will go in the positive direction. If you are in the negative x-axis, you will go in the negative x direction. Now, on y-axis, if you take a point 0 comma y, then the gradient is 0 comma minus 2y, which means that if y is positive, because minus 2y is negative, the gradient vector will point in the reverse direction. So therefore, these arrows are pointing downwards, which is the negative y direction. On the other hand, if y is negative, so if you are here on the negative y-axis direction, then minus 2y will be positive, therefore you will point towards the positive direction. Okay? So that's what is happening in this picture. That's how you plot a gradient field. Okay. Or a vector field. So now let us look at how chain rule facilitate us to compute gradients of certain functions. Okay. So suppose f is a function from R3 to R and it's a differentiable function, and let Ct be a differentiable curve in R3. Okay, which is the domain of f. Now you define this function ht equal to f of Ct, which means that you are looking at the values that the function f takes on this curve. So instead of looking at values on all of R3, you just focus on this particular curve in R3 and you see what values the function takes on this curve. So this can also be written in this notation h is equal to f composed with c. Okay. So by chain rule, you know that h prime t is nothing but gradient of f ct dot with c prime t. Right? So earlier when we were talking about chain rule, we wrote in terms of matrices. Okay? So there grad f was a row vector and c prime t was a column vector. But that can also be written as dot product of two vectors, right? Which is this and this. So this comes from chain rule. So the expression on RHS is the dot product of these two vectors. So what do? You take the gradient of f at the point Ct and dot product it with C prime t, which is the tangent vector at the point t. So now, if fct attains a minimum at t equal to t0, so from one variable we know that if h prime t, if ht, which is f of ct, if it attains a minimum, then the derivative should be 0, right? So therefore at this point derivative should be 0. But what is this derivative? This derivative is nothing but the dot product of gradient with C prime at the point T naught. Therefore, what do you mean by dot product being 0? That the two vectors should be orthogonal to each other. Hence, the vectors gradient f at C T naught and C prime T naught, they should be orthogonal to each other. Right? And same thing will happen when it's the maximum, right? Even in the case of maximum, h prime will be 0 and the vectors will be orthogonal. Alright. Let us look at this example. So suppose your function fxyz is e to the xyz and the curve is t, 2t, 3t. What is ht? From the previous slide, it is f composed with c at t. So you substitute these coordinates x equal to t, y equal to 2t and z equal to 3t in this function. You get e to the 6t cube. So if you take the derivative of this function, by chain rule you get 18t square times e to the 6t cube. Now, this is by directly substituting the Ct here and then taking the chain rule of one variable. But if we use the chain rule from the previous slide, h prime t is nothing but gradient of f at this point dot product with c prime t. What is gradient of f? Gradient of f you can compute. The first component will be the derivative, the partial derivative of f with respect to x and so on. So if you evaluate this gradient at the point Ct, you replace x by t, y by 2t and z by 3t. This is the vector you get. Right? Now, what is C prime t? C prime t is I plus 2j plus 3k, right? You differentiate it component wise. So if you take the dot product of these two vectors, you get 18t square e to the 6t cube, which is same as what we got initially. So this example is kind of a verification of what we studied on the previous slide. So in the first bullet, we substitute Ct directly and write h as a function of t alone, use mth101. And in the second case, you use the gradient definition, which we got in the previous slide. Alright. So now let us look at the relationship between gradients and what is called a directional derivative. Okay. So this concept of directional derivative is quite important and you should pay attention to the next two slides specifically. So let f be a differentiable scalar valued function on R2 or R3. So you should understand this terminology. When we say scalar valued function, that means it takes real values. Okay. What is directional derivative? The directional derivative of f at the point x in the direction of a unit vector b is the rate of change of f along the line x plus cv. What is the line x plus cv? It's the line passing through the point x with the direction b, right? So if you walk along this line how does your function change? That's what we mean by directional derivative. Okay. So suppose you take Ct to be x plus Td. So this is a curve in R2 or R3 depending upon what is the domain of f. And you take Ht to be f of Ct, meaning you are only focusing on the value of the function f along this line. Then h prime t is equal to gradient of f Ct dot C prime t from the previous discussion. And hence the directional derivative of f at the point x in the direction of the unit vector v is given by h prime 0, right? And what is h prime 0? It's gradient of f at c0. What is c0? c0 is x. So you get gradient of fx. What is c prime t? C prime t is the vector v. So you get v. So this is the directional derivative of f at the point x in the direction of a unit vector v. And it is denoted as df xv. So the first symbol in the bracket is the point at which you can compute the directional derivative, and the second bracket is the direction in which you compute the directional derivative. Now, when will this dot product be maximum? What is dot product of two vectors? It's the product of their norm times cosine theta, where theta is the angle between them. So when will that quantity be maximum? When cos theta is 1 plus 1, right? When cos theta is plus 1, that means theta is 0. So the directional derivative of f at the point x is maximum when the direction of v is same as the direction of gradient, right? And when will it be minimum? It will be minimum when cos theta is minus 1, which means theta is 180 degree or pi, which means that they are in the opposite direction, right? And what is the direction? So if your vector is this, what is the unit vector in that direction? You just divide by the norm, right, of the vector. That makes it unit. And similarly, what is the opposite direction of gradient f? What is the opposite unit direction in gradient f direction? It's negative of gradient f divided by norm of gradient f. Of course, when we do this, we are making an assumption that gradient is non-zero. Okay, because if gradient is 0, then you can't do this thing. So if gradient of this function is 0, then the directional derivative is 0, right? So if the directional derivative is 0, then we are not doing these, right? Because in any direction it will come out to be 0. Okay. So now let us look at a few remarks about directional derivatives. So directional derivative, recall, is given by gradient of fx dot the direction. Remember, v is a unit vector. So if v is v1i plus v2j plus v3k, suppose v has these components, then by definition, what is the directional derivative? It's gradient f dot v. So gradient f has components fx, fy, fz, and v has components v1, v2, v3. So if you take the dot product, you get fx v1 plus fy v2 plus fz v3, and you evaluate it at the point x, right? Now, if v is one of the standard basis vectors I, j, k, then the directional derivative in the direction v is nothing but the partial derivatives, right? Because if you take gradient of f dot I, you get fx. If you take gradient of f dot j, you get fy. And if you take gradient of f dot k, you get fz. So in the standard basis directions, gradient is nothing but, directional derivative is nothing but partial derivative in that direction. That is, fx is the directional derivative of f at x in the x direction. I am sorry that this positive should not be there. In the x direction, which is I. In other words, fx, which is the partial derivative of f with respect to x, is the rate at which f changes when one moves in the direction of x-axis starting at the point x. So ignore this positive here, positive should not be there. So you start at the point x and you walk along the x-axis direction. That gives you the, and if you compute the rate of change, it gives you the partial derivative with respect to x, right? So directional derivative in particular is nothing but partial derivatives when your direction is one of the standard directions. Okay. Now this part is important. If u, v, w are three linearly independent vectors, then any vector in R3 can be written as a unique linear combination of these three vectors. This you have seen in your linear algebra course. Therefore, if I compute the directional derivative in the direction of capital V, by definition, it is gradient f dot V, but V is equal to alpha u plus beta V plus gamma w. Now you use distributivity of dot product. So you get, and you bring the scalar out, you break it into three terms. But the first term, gradient fx at dot u, is nothing but the directional derivative. So what have we done? We are able to compute the directional derivative in any direction using the directional derivatives in these three linearly independent directions. So once you know directional derivative in any three linearly independent directions, you can compute directional derivative in any direction. Right? So hence directional derivative in any three linearly independent directions determine all the directional derivatives. This is quite crucial. And note that all the above statements can be talked about for a function on R2 in which the third entry will be dropped. Okay, so you won't have a k coordinate component. Okay. So let us look at this example. Compute the directional derivative of fxy equal to x square plus y square at the point 1, 1 in the direction of the vector 1, minus 1. In which direction does f increase fastest and in which direction does f decrease fastest at this point 1, 1. So suppose I call this point 1, 1 as x. Now remember, when you compute directional derivative, you want a unit vector because you want to compute rate of change, right? So it has to be a unit vector. So first of all, the given vector has to be converted into a unit vector. So this is a crucial step. So you take V to be the normalized vector, which is 1, 1 divided by square root 2. What is gradient of f? It is the partial derivative with respect to x is 2x, partial with respect to y is 2y. So if you compute at the given point, you get 2, 2. So if you look at, so I'm sorry, there should be a negative 1 here which I have missed. So b is 1, minus 1, 1, minus 1. So you can see that if you compute the dot product of this vector with 1, minus 1 by square root 2, you get 0. So the directional derivative in this direction is 0. Now, What is the direction of fastest increase? It's the direction of the gradient, which is 1 comma 1, and fastest decrease is in the direction of negative gradient, which is this direction. Few notes. So here you may notice that I have not normalized these vectors. Okay, because the question did not ask about the unit direction in which the increases fastest or decreases fastest. It just asked me for a direction, so I need not normalize them. So, but normalization of vector is important when you compute the directional derivative. Should keep this in mind. So, if the directional derivative is 0 at a point in the given direction, then there is no change of the function by moving along that direction. Right? In this example, at any point x comma y, f increases fastest in the direction x comma y because that's the gradient. Right? What is the gradient of this function? It's 2x comma 2y. So at x comma y, the fastest increase is in the direction of x comma y because 2 can be ignored. Right? It says the direction, so you can scale it. And decreases fastest in the direction of negative x comma negative y. Right? Which is the negative gradient direction. We'll look at a picture in the next slide. So, let me go back. No, I don't have to go back. This is the function, right? X square plus y square. What are the level curves of this function? They are nothing but these concentric circles, right? What are level curves? You set function to be equal to a constant. So when I set it equal to a constant, then I get these circles, right? So I have drawn these circles with increasing radii. So the innermost has radius 1, then 2, 3 and so on. Okay. So if I take the point 1 comma 1, there are three directions. One is the 1 comma 1 direction, other is the negative 1 comma negative 1 direction, and third is 1 comma minus 1 direction, which was the vector given to you. So the green vector, which is 1 comma 1, is the direction of fastest increase, right? Because in this direction f increases fastest, isn't it? Because it keeps on increasing. You're walking across the concentric circles. When you go in the reverse direction, you are decreasing fastest, right? Which is the violet direction or purple direction. And the blue direction, which is the given vector where directional derivative was 0, if you walk in this direction, then you neither increase nor decrease. And note that this vector is actually perpendicular to the gradient vector, which is this green direction, right? These two vectors are perpendicular to each. So this picture should tell you how things are related. What do we mean by fastest increase? What do we mean by fastest decrease, and so on. Okay. So now let us finally look at one more example. So let us compute the directional derivative of this function at the given point in the direction of this vector. In which direction does f increase fastest and in which direction does it decrease fastest at the given point. So suppose this is the point, vector is not normalized, so you normalize it, you get the gradient. In this case as well, the directional derivative comes out to be 0. Fastest increase is in the direction of gradient and fastest decrease is in the direction of negative gradient. So you get minus 2j, which is nothing but negative y-axis, and fastest decrease is in the direction of 2j, which is positive y-axis. Again notice that directional derivative 0 means that there is no change if we move along that direction. And this is important, the second point. When the direction of maximum increase or decrease is asked, there is no need to normalize the direction. Unit direction is required for computing directional derivative since it is the rate of change. So let us stop.